Strictly speaking, a continuous function is a function that can be drawn without, that should be your pencil lifting off the paper. There is no hole, no gap, no vertical asymptotes. That's like this guy. If I want to draw him, I put my pen down and I can just trace him without lifting my pen up. This is a continuous function. It's a continuous graph. Here is a hole. So that means I take my pen, draw him, jump over the hole, and then continue. They call this a gap. I call this a jump discontinuity, but you can call it a gap if you like. Don't care which one. And that says I've got to jump either up or down to get to the next piece of the graph. So I can have a hole, which is a discontinuity. I can have a jump or a gap. That's a discontinuity in the graph. I can have a situation where I have a vertical asymptote. Now I have to jump over the asymptote to continue drawing this graph. So I can have a vertical asymptote. And notice it says, at C. Continuity is only at a specific point. Because if I were to take a look at this piece of the graph here, I can draw this piece of the graph without lifting up my pen. He's continuous. The minute I include x equal b, I have a jump. He's continuous except at x equal b. If I include this piece of the graph, this whole thing has two discontinuities, a hole at x equal a and a jump at x equal b. By the way, this hole is called a removable, and here's the big word, singularity. He is a removable problem. Holes are removable. I've removed the issue. So the limits exist. I removed the problem. And by the way, when you get into graduate level calculus, it's like we can find something which is continuous almost everywhere. And all the rules that we've used can be used on these things, where if I'm down in our calculus and I'm down in the regular engineering calculus, it's like I can't do this on a a function that has a discontinuity, especially if the discontinuity is included in the region where I'm working. So in other words, there's some things I could do as long as this guy was present. If I just go from here to here, I could do anything I like. But include that discontinuity, there are things I can't do. So he is removable. Now that's what would make him not a problem? If I could fill that hole in. If you give me a y value that fills the hole in and makes it not a problem. If you could fill that hole in. There's nothing I could ever do with this. I can't ever remove this guy. Why? Because he is a number divided by 0. Remember, the hole is 0 divided by 0. That's how we get him. The asymptote is a number divided by 0. That's why he's called removable. Because why? We removed the problem. We used algebra to cancel it out, to remove it. That's what makes it removable. Here, there's nothing I can do to remove this thing. He's there forever and ever. Why? Because he is, and in fact that number technically can't be 0. I'll have a number divided by 0 which will always be undefined. It's that good old indeterminate form. So here we go. This is the mathematical definition of continuity. We normally are not going to have to worry about this, but we again have to cover it for some of the stuff we're going to do. And that's this. A function is continuous at C. We're only talking about a single number. If all three of these conditions are satisfied, all three have to be satisfied. F of C exists Well, if I take a look at my two graphs above, f of A does not exist. That means no holes, no VAs. Because if I put x equals c, I get something which is undefined. So no holes, no VAs. The limit as x approaches c of f of x exists. Well, here it exists. Where it doesn't exist. Right there. No jumps. And here's the kicker. That's not enough. And you're going to say, well, why is that not enough? Well, here's the problem. You say, well, it has a hole. That's true. But does f of c, if this is c, exist?
Yes.
Yep, it's that stupid solid dot. So f of c exists. So we have to have the kicker to take care of this condition right here. The limit as x approaches c of f of x equals f of c. That means the dot is in the hole. The dot's in the hole. If the dot's in the hole, it's continuous. If it's not in the hole, it's not. Forces the dot to be in the hole. As long as this guy's not in the hole, the guy is not continuous. Why? Because you go, and then you have to go up here, do the dot, then you have to jump back down and finish the graph. But it forces the dot to be in the hole. So that dot is in the hole. And that is for this condition right there. Because if f of c is defined, it better dang well be in everybody comes together. And see, this would be f of c. So this is what we call necessary and sufficient conditions. These two are necessary, but they're not enough. You have to have the third one in order to basically force that dot to be in the hole so that you can draw it without lifting your pen. Ooh, that's ugly. Now, here's the question. Do we